I'm gonna make a, a little bit of a summary for you of some things we know from special relativity. Here they are. We have time dilation. And remember, the thing about special relativity is that everything so far seems to be governed by this factor of gamma. Gamma is 1 over 1 minus v squared over c squared, but the denominator is in a screw. And there's a beta in there. We can write it as beta instead. 1 over 1 minus beta squared. Screwed. Okay, so I'm going to draw you a graph of time dilation that I hope will make some sense. Now, this is beta on this axis, which again is the speed of the object over the speed of light, and beta doesn't get bigger than 1. So here's time dilation, which I'll define as the time that you see divided by the proper time, and I will use the red to represent blood and sacrifice. It is the classical solution to this problem, and I'll give you a 1 here where those guys are the same. So the classical thing says time is time. What do you want, right? Seafoam green comes in as rebirth, and it says now we're actually going to get longer time depending on what's going on. So you see things going more slowly, and it's like almost exactly the same, and then it gets big, and then it gets really big, and then it goes to infinity, because we're never going to get to 1, right? So this is relativistic. And in a word, that's real, that's what actually happens. And this red is classical, where time doesn't depend on how fast you're moving, which seems like a pretty stupid idea in the first place, but it turns out to be true. So the next thing that we can do is we can mark some interesting points. I always think it's interesting to find out when time doubles, and I'll put a dotted line over here and say that time doubles at, let's go down here, this is supposed to be 86% the speed of light. All right, and then we could also find out where time goes up. Now this is going to be hard to see, so I'll do it in purple. We could find out where time goes up by 1%. So I'll put a dotted line over here. It turns out it's about right there. Very hard to see at, oh, sorry, this isn't 86. It's supposed to be 87. 87% the speed of light. And here at 14% of the speed of light, we get a very slight increase, and I'll put an arrow to that and say it's 1.01. That's where I would say the onset of relativistic effects begin. Then we could also look at length contraction. The effect... This is not an introduction to any of these topics up here, simply a summary. The effect of length contraction gives you something like this, where this is again beta, and it's going to be V over C, and I'll give you length here. This is how long something actually appears to be in meters. And I'm going to say length contraction of a meter stick to give us something concrete to work with, but everything will be everything will be scaling the same way. So the classical solution to the length of a meter stick is it's a meter. Okay, that's classical. Your meter stick is 1 meter long. Great job, classical physics. But in, you know, the speed limit in the universe that we say is where beta is in 1, v is the speed of light. You can't get there. Seafoam green comes out here. This is the relativistic solution, and it says, no, it's going to be like this. It's going to be like, boom! And in fact, if you do reach the speed of light, then you will find that your meter stick doesn't have any length at all. So we can call out a couple interesting points here. I always think it's interesting to find the halfway point or the doubling point right here. If you've got 1/2 of a meter, let's see, we'll write it there, 1/2 of a meter should happen at 86% the speed of light, 0.86. So maybe my graph isn't quite shaped right. It's kind of right. It's pretty close. And then we also might wonder where we're 1% off. And again, 86, dang it, it's 87. I think I keep subtracting from 1, making myself confused right there. The 1% difference, and we can kind of put that in quotes, this is sort of like 0.99 meters, kind of, and that's going to happen at 14%. The speed of light. All right, good. So that's where stuff happens. That's where classical starts to break down, and here classical is really, really screwed up. I want to look next at velocity addition. And this is where our lecture is actually going to take off a little bit here. Velocity addition, and I'm going to graph beta as a function, well, it's v over c. That's actually going to be my y-axis, and this axis down here is the time spent accelerating constantly. Let me see if I can spell. Accelerating at constant rate. Now, we don't get to put any ticks over here, but I do want to tell you that the classical solution says the more time you spend accelerating at constant rate, the faster you'll be going. This is classical physics right here, and you know that velocity final is, well, saying that your velocity initial is 0 lets you say it's just your acceleration times the time that you have spent accelerating. So of course we're going to get a beautiful linear graph right here, but you know that there's this ultimate speed limit to the universe, and that's at beta equals 1, and so we better not get anything crossing that in the relativistic or true, real. Let me label this guy here. This is relativistic. And that's actually what happens. Deal with it, people. So you know that if you speed up in a real rocket and you're spending more and more time accelerating, then you're going to get a line that looks like this, but at some point it's going to diverge from there and you will spend more and more time accelerating. You will actually be accelerating here. Spending more and more time accelerating, but you will get faster and faster, but just never, in fact, crossing that speed of light. It's like getting closer and closer to the finish line, but never quite getting there. There's an interesting problem about that. But this is the relativistic, or actual behavior of something that is speeding up more and more and more. So this troubles me because it makes me think that if I spend more and more time speeding up, I'm not getting anything for that. I'm clearly not getting any substantial speed. So I could be at 99% the speed of light, and I could speed up a ton, what would have put the amount of energy into it that would have doubled my speed, and I won't nearly double my speed because I can only get to the speed of light, or just below the speed of light. So that's really frustrating. Let's see if we can make some sense out of it with momentum. My argument is that momentum is going to take care of us here, because as we get closer and closer to the speed of light, something magical happens. I'll make you a graph of relativistic momentum as a function of the speed that we have. So here we go. Momentum P, speed down here. This is going to be beta, which is v over c. Sorry, that's a really nasty beta. Classically, we find that, oh, let me put a tick mark here at 1. Classically, we find that we would expect that if we have, wait a second, get a classical equation up here. You talk about linearity. The classical equation says P is mv. Okay, m times v, just a little momentum. Watch this. You go out here and you'd be like, that is the prediction for how much momentum you have. However, something beautiful happens. It turns out that the quantum mechanical, no, what the heck? The relativistic solution right here says you can't get faster than that. In fact, your momentum will continue to increase even though your speed's not increasing much. And we get this behavior right here. This is, again, classical prediction. And as we get closer and closer to the speed of light, relativistic effects become more and more significant. The relativistic or actual result is shown right here in seafoam green, the color of hope. That right there is going on. But at the same time, now let's reconcile this. Here's our time spent accelerating at a constant rate. I'm just going to cover that up so we can see this a little bit better. If we spend some time accelerating at a constant rate, our speed doesn't increase, but as our speed gets closer and closer to the speed of light, our momentum increases like crazy like this. So we've got this tapering off here and this crazy going right here. It turns out that momentum continues to increase linearly. So what if I make a graph of not speed as a function of time spent accelerating, but momentum as a function of time spent accelerating? Wow, this is supposed to be momentum as a function of time spent speeding up. And I'm going to put speeding up in quotes there because I'm not sure we're actually going to be gaining speed much. We'll definitely be accelerating. And the beautiful thing is, we would expect in classical physics for the momentum to increase linearly, you spend more and more time speeding up. And look, it's the same graph. I mean, it's supposed to be, but I can't draw a straight line. Classical and relativistic finally agree. Classical and relativistic say if you spend more and more time speeding up, you're going to get more and more momentum linearly. And the only way we can do this, see, you know that V's got this problem. V says we're not speeding up quite enough, but I'm going to define momentum a little bit differently. Momentum real or relativistic, put an A in there or not, I don't really care what you do. Momentum real is going to be gamma times m times v, or it's sort of gamma times momentum classical. This is the momentum that you used to know, m times v, just a little momentum, but I'm going to say, look, vector here, vector there. If we multiply it by gamma, then we get the real momentum. And some people don't like this. I frankly don't really like this. So I'd like to just, redefine mass. Okay, watch this. I'm going to say the true momentum, real relativistic momentum, is going to be, well, it's gamma times m times velocity. And this is actual velocity, and it would be less than the speed of light at all times. But gamma times m is our new mass. And I'm going to call that, watch this, I'm going to call it mass. So I get back my original momentum equation. I can still say m times v, just a little momentum. But I have to redefine. Mass is now defined as m naught. Ooh, this is something I'm going to call rest mass. And then I have to divide it by 1 minus, well, beta square, and this all has to be in a screw. That's gamma screwing up my mass. So I'm saying as you get closer and closer to the speed of light, you can't speed up anymore. Look at this graph right here. As you get closer and closer to the speed of light, you can't speed up anymore because your mass is getting bigger and bigger. But the consequence of that is you carry more and more momentum, disproportional to your actual speed because your mass is going crazy heavy. Heavy. Okay, I don't think I have anything else to say about this. We have just modified mass. Look, mass is not the mass that you thought you knew and probably once loved. Goodbye. By this factor of gamma. Gamma is 1 over 1 minus v squared over c squared, but the denominator is in a screw. And there's a beta in there. We can write it as beta instead. And beta doesn't get bigger than 1. So here's time dilation, which I'll define as the time that you see divided by the proper time. And I will use the red to represent blood and sacrifice. It is the... I'm gonna make a little bit of a summary for you of some things we know from special relativity. Here they are. We have time dilation. And remember, the thing about special relativity is that everything so far seems to be governed 1 over 1 minus beta squared. Screwed it. Okay, so I'm going to draw you a graph of time dilation that I hope will make some sense. Now, this is beta on this axis, which again is the speed of the object over the speed of light. Classical solution to this problem, and I'll give you a 1 here, where those guys are the same. So the classical thing says time is time. What do you want, right? Seafoam green comes in as rebirth. And it says, now we're actually